Hi everyone, and welcome to today's podcast. For today, we're exploring into some key concepts and differential equations that we covered in modules 1 and 2 of our course. We'll be sharing our reflections on topics like directional fields, classification of differential equations, autonomous differential equations, and many more. So, let's introduce our members, Iya, Aya, and John. Thanks for joining me today, everyone. To kick things off, let's start with our Module 1 topics. We covered a lot of foundational concepts here. John, what was your experience with directional fields and the classification of differential equations?
Thanks. Directional fields were actually pretty interesting. I found that they give us a good visual representation of solutions without actually solving the equation. This visual approach helped me understand how solutions behave over time, which can be pretty complex otherwise. As for classification, learning to differentiate between linear, nonlinear, exact, and separable equations was crucial. Knowing the type of equation helps us decide on the most effective solution method.
That was great, John. I felt similarly. Directional fields provided a new way of looking at equations that helped me grasp the behavior of solutions early on. It's like having a map before even starting the calculations. And understanding classification is like knowing which tool to pick for each task. It really builds a strong foundation. So let's move to autonomous and separable differential equations. How did these topics resonates with you, Iya?
For me, autonomous equations stood out because they model real world situations where change only depends on the state itself, not on time. It's fascinating to see how they apply to things like population growth or decay. Separability also simplifies solving differential equations since it allows us to split and integrate them. I feel that mastering these two types has been a huge boost to understanding the course material.
Absolutely, Iya. Autonomous equations have so many real-world applications, which makes them easier to relate to. And separable equations are satisfying to work with because they break down complicated problems into manageable parts. Moving forward, let's talk about the linear and nonlinear differential equations. Aya, how did you find these topics?
Linear differential equations were very structured and predictable, which I appreciated. They follow a specific form and have established solutions, making them relatively straightforward. Nonlinear equations, on the other hand, were more challenging. Their solutions can be unpredictable and often require numeral methods. But I found that understanding both types is essential, especially because nonlinear equations describe more complex, real-world phenomena.
That's a great point, Aya. Linear equations feel very methodical, while nonlinear equations add that layer of unpredictability. And lastly, for Module 1, let's talk briefly about the exact differential equations. I personally found that identifying exact equations made it possible to integrate them directly, which was helpful. Does anyone have thoughts on that before we move to Module 2?
I agree. Exact equations gave us a way to solve equations without guessing functions, which saved a lot of time. It was nice to see a method that applies so directly to certain problems.
Absolutely, John. Now let's dive into Module 2. Iya, can you share your reflections on homogeneous equations with constant coefficients and the round scale?
Sure. Homogeneous equations with constant coefficients were interesting because they are consistent in form, which makes solving them systematic. They help us work with solutions that have exponential functions. As for the Wronskian, it was a bit challenging at first, but I came to appreciate it because it tells us if solutions are linearly independent, really useful when we're solving higher order equations.
Yes, the wrong scan can feel abstract, but it's such a powerful tool. I felt that both topics gave us more insights into how solutions behave. Moving on, Aya, let's talk about the nth order linear differential equations and non-homogeneous equations. What are your thoughts?
That nth order linear differential equations were intense but rewarding. They extend our understanding from first and second order equations, showing how solutions can get more complex. Non-homogeneous equations also challenged me, but learning to solve them made a lot of practical sense, as these types of equations show up frequently in applications.
That was nice, Aya. Those higher order equations definitely add complexity, but they also prepare us for a wider range of applications. So, John, could you give us your thoughts on the variation of parameters and second order differential equations?
Variation of parameters was a real eye-opener because it's a flexible method we can apply when other methods don't work. It's complex, but the versatility is worth it. Second-order differential equations especially were practical as they model many physical systems, from oscillations to electric circuits.
That was right, John. The variation of parameters may be challenging, but it's an essential tool in the toolkit. Now, let's finish up with the Laplace transformation. Iya, how did you find it?
Well, the Laplace transformation was both challenging and fascinating. It transforms differential equations into algebraic ones, which simplifies solving complex equations, especially with initial conditions. I can see why it's such a powerful method in engineering and physics.
I completely agree with you, Iya. The Laplace transformation has been invaluable for tackling problems that would otherwise be too complex to solve directly. Well, that wraps up our reflections on modules 1 and 2. Thank you so much for sharing your thoughts, everyone. I think we've all gained so much a deeper understanding of differential equations, and it's been great to reflect on the journey together. Thanks to everyone for tuning in, and we'll see you next time.